Hey, this is DW. We had a technical glitch this morning. I had done something with my laptop over the past few days where the sound was muted, and so this morning's lecture, the audio was not captured. The video was, but let me just redo a voiceover. The advantage to you is the video will be a little bit shorter than lecture this morning, but there won't be the energy we had in class. So let's get started. So the point in class that I made about the spectrum is, let's pretend this was an experimental spectrum, and we've received this spectrum. We wanted to know what these various peaks were, and we would do the math to come up with the selection rules. So why would we have these selection rules, delta n equals 1, 3, or 5? You did the math from sort of first principles, looking at the wave function and computing the transition dipole moment integrals. But is there a faster way? Is there a way that we can look at the symmetries of the wave functions and come up with the same result of allowed and forbidden transitions, so that if we were to assign these peaks, we would know that none of these peaks is a quantum jump of delta n equals 2 or 4, that these have to be odd quantum jumps? We can look at the symmetries of the wave functions, and the properties of symmetric functions will help us to understand what the results of those integrals will be. If you'll notice here that we have the properties of even and odd functions, and we'll define those in a second. But this is a very important thing for you to take note of. In fact, write this down clearly or circle it in your notes, that the integral over all space of an even function, soon to be defined, okay, an even function is non-zero, and the integral over all space of an odd function is 0. So if the function is odd, then you integrate it over all space, you're going to get 0 by definition. And so this is the annotations we did in class, and so we'll walk through these. These even and odd functions can also be the products of multiplication. So for these multiplication rules, if you have a function f of x that happens to be even, and you multiply that by g of x, what happens to be even, the result is even. This multiply symbol here is the direct product. So it's every corresponding value in that function multiplied by its corresponding value in the next function, and so on. It's not you're not summing them. It's not like matrix multiplication. It's just direct product. You're just taking every value in that function times its corresponding value, the same x value, in the next function, and carrying those multiplications through. So if we just abbreviate and get rid of the g's and h and f, we have even function, direct product with an even function, the result is even. You can think of this as like the multiplication rules of positive and negative numbers, because again, those function results, f of x is going to be either positive or a negative number. And so if you have positive numbers times positive numbers, you end up with positive numbers. But if you have a positive number times a negative number, you end up with a negative result. And then this carries through to the whole function. So if you have an even function times an odd function, you end up with an odd function. And then if you have two negative numbers multiplied by each other, they become positive. Likewise, if you have an odd function times an odd function, the result is even. And then if you chain these together, if you have three odd functions together, you can evaluate them. And it's good practice to do this from right to left. So you have the first product here, odd function times an odd function gives an even result. And then you have this odd function multiplied by the result of the first multiplication. So odd times even then gives odd. And you can chain these together an infinite number of times. We will typically use 3, but sometimes in combination bands and overtones we end up with multiple ones, more than 3. So let's now apply this to our particle in a box problem. Before we did that, though, we looked at the properties of odd and even functions. And so these are the definitions here of odd functions. So if the definition of an odd function satisfies this criterion here. So if I'm looking at an odd function like x here, and I plot f of x equals x, and I look at the symmetry of the function, notice if I go in the negative direction in x, then the function is the opposite sign than it is in the positive direction of x. So I go forward a certain amount in x and evaluate the function. and then I can go negative in the negative direction, that same distance, and evaluate the function. And this is the same magnitude but opposite sign of this point here. And so that satisfies this definition, and so that means this is an odd function. Let's look at x squared. F of x equals x squared. If I go in a forward or positive direction in x and evaluate it, so this is centered on 0. If I go in the positive direction and evaluate the function x squared, and then I go that same distance in the negative direction and evaluate it, I get the same magnitude and same sign. So that satisfies this definition, and that means that x squared is an even function. And we can do the same thing with our wave functions. If we were to look at the ground state wave function, so n equals 1, looks like this, centered on 0. And notice if I go in a positive x direction, a certain amount, and evaluate the function, and I go that same distance in the negative x direction and evaluate the function, I get the same sign, the same magnitude. So that means that n equals 1 is n equals 1 then is even. And if I look at n equals 2, again centered on 0, has a positive region, it crosses over, it has a negative region here. And so if I go a certain distance in x and evaluate the function, I get a negative value. I go that same distance in the negative direction and evaluate the function, I get equal and opposite numbers. And so that satisfies the definition for an odd function. And so n equals 2 is odd. So we can come up here to our transition dipole moment integral, and we can fill in the symmetry of the n equals 1 and fill in the symmetry of n equals 2, and we know the symmetry of x is odd, and we can do our multiplication rules. So we have an odd function times an even function gives an odd result, and then this odd here, the n equals 2 symmetry, multiplied by that result gives an even result. And the integral over all space of an even function is not equal to 0. Therefore, this transition is allowed. Now, it took us an enormous amount of math to get this result, but we could tell you at least that it was non-zero on a cocktail napkin. And so that's why we have this box here. This is our cocktail napkin computation of the selection rule, showing that the transition from 1 to 2 is allowed. We can do the other selection rules shown on this sheet. Again, the symmetry of the n equals 1 is even. The symmetry of x is odd. If we go back to our previous slide, looking at the wave functions, we see n equals 4 is going to be an odd function. And so then we do the multiplication. I'm just using O for odd and E for even. So odd times even is odd, and then odd times odd is even. So the integral over all space of an even function is not equal to 0. So therefore, the 1 to 4 transition is allowed. Looking at the 1 to 3, this is a delta n equals 2. Okay, we have an even function for n equals 1, and 3 is an even function, and x is odd. So multiplying these through, I have odd times even is odd, even times odd is odd. So here we have an integral over all space of an odd function, and by definition that's equal to 0. Therefore, this jump is forbidden. So this would tell us that in that experimental spectrum that we had back here, none of these peaks results from a 1 to 3 transition, because that would be a delta n equals 2, and that would be forbidden by symmetry. So knowing something about the symmetry allows us to understand why this rotational vibrational spectrum of CO2, it looks different in the left and the right. This one over here has a gap in the middle. This one has a peak there in the middle, and we can understand why that is using symmetry arguments. It also tells us why CO2, this particular peak for CO2, is so nice and beautiful compared to water. So water is just a big mess. The selection rules for water are wide open, and I asked why, and the class accurately suggested that it might be related to water being bent versus CO2 being linear. The CO2 being a linear molecule is very much more symmetric than water being bent. Water is an asymmetric molecule. It also tells us a little bit about here's an infrared spectrum of automobile exhaust, and symmetry can tell us why the selection rules for the Raman active mode, this symmetric stretch in CO2, will not allow it to absorb infrared light, but will allow it to scatter light in the Raman effect. So symmetry can explain these complicated spectra of three-dimensional molecules, and we introduced it just today in terms of one dimension, the particle in a box. So the need for symmetry, we've looked at the particle in a box. It's easy. Even the particle on a ring is easy, still one dimension, but it's a rotational system. The hydrogen atom is not so easy. That's why I put it in lowercase. But then all molecules are complicated, even a diatomic. We need molecular orbital theory. It helps us understand diatomic bonding. But then symmetry helps us understand everything, that's a molecule up. So if the molecule is symmetric, like ammonia or even water has some symmetry. It's just what they call an asymmetric top. Still, it helps us understand the spectroscopy of water, ammonia, benzene, these symmetric molecules. And let's say we have a very huge asymmetric molecule like DNA. Well, if you've got inside there those base pairs that are planar, the planar nature of those base pairs, that's symmetry. And so even in a huge, complicated asymmetric molecule, we can understand something about its bonding, its chemical nature, and its spectroscopy by looking at local symmetry. So the planar species, we can understand them individually by looking at their reflective nature from the sigma planes, from their reflective planes. So let's walk through this. What is the main point of the connection of symmetry and spectroscopy? Well, we've already identified that it's the selection rules that are really important. We want to know what peaks are in the spectrum, what they're related to. We also want to know if those, what the allowed transitions are, what the forbidden transitions are. And so selection rules are really what we're after. We get those from the direct product tables. And the direct product tables really, it's easy in the particle in a box. We just have even and odd functions, and it's a one-dimensional system. You can sketch the function out by hand. But when you get to a three-dimensional molecule like water or benzene, you have, like, I think benzene has 12 different types of symmetry. So its vibrations, its rotations, and everything are going to be one of 12 different types of symmetry. And so then you need to know the products of all of those. We have, instead of just even and odd, we have A1, A2, A1G, A2U, EG, EU, T2G. We have all of these different symmetry designations. And the multiplication tables help us understand how the symmetry behaves when we multiply these different symmetries together. So this direct product table I call a Rosetta Stone. The symmetry operations would be unintelligible if you didn't have these direct product tables, just like Egyptian hieroglyphics were unintelligible until we found the Rosetta Stone. And we get those direct product tables using the symmetry species that we find in the character tables. The character tables define the symmetries of all molecular motions, all the molecular orbitals, and all the equivalent nuclei in an NMR experiment. And it also can give us intensity patterns in the infrared. Those come from those symmetry elements in the character tables. And we can't find the character table without knowing the point group. The point in the point group is the center of mass, and the group is sort of a mathematical group of symmetry operations. We don't know how to get the point group without the structure of the molecule. And so we need the geometry to identify the point group, and we get the geometry from the Lewis dot structure coupled with the valence shell electron pair repulsion theory, or local bond theory, or hybridization. So this ties the spectrum all the way down to the Lewis dot structure. So you need to be good at Lewis dot structures. You need to be good at coming up with the three-dimensional shapes of a methyl group. You know, you see that tetrahedral carbon in the middle because it has 4 electron domains. You need to be able to come up with those geometries so that you can find the point group. Once you have the point group, you get the character table. And you get all the symmetry species of the motions, the molecular orbitals, etc. And the direct product tables tell us how those different molecular motions or molecular orbitals will interact with light. And once we know the direct products, we get the even or odd functions in the integral result, we can determine whether that transition is going to be allowed or forbidden by symmetry. So this is the whole scheme of spectroscopy, tying a spectrum and its selection rules all the way down to the Lewis dot formula. And so you need to be good at doing these Lewis dot structures. So review your GenChem. So I've given you this free resource up here. This is an OpenStax book. And so let's go. If you were to click on this OpenStax book, you could find the valence shell electron pair repulsion theory and hybridization. You could see those tables. In fact, let's just do that. This is a really a fantastic free resource for not just chemistry, but history and government, economics, and so on. So if you need a free textbook, let's say you were foolish and you sold your book back. So you were foolish and you sold your book back, and you now wish you had your Gen chemistry book to refer to. You can go here to OpenStax and have a free version of the freshman chemistry text. So here we are viewing the text online. It's totally searchable. We can type in here hybridization. I'll just type in hybrid. That ought to get us something. I'll get a Prius hybrid. Yeah, so let's look here. So we're talking about Lewis dot structures, orbital overlap. We start seeing the different types. Let's go to valence bond theory. Hybrid atomic orbitals. This should be looking familiar to you, the different Lewis dot structures. You're going to need to know this because I'm going to give you this molecule and ask you what the symmetry is. And you need to know that those F atoms are right on top of each other and should reflect through. And then this table is critical. And so you have the regions of electron density. If there's 2, it's linear. 3, it's trigonal planar. Now these are the electronic structures. This is the electron cloud around that central atom. But like in water, so there's 4 electron domains around that oxygen, 2 lone pairs and 2 bonds. And so you put hydrogen on each of those 2. And so it's not a tetrahedral structure for water. It's a bent structure. So you label the structure based upon the atoms, where the atoms are, but you need to know the electron cloud around that oxygen so that you know what the angles are for those 2 hydrogen bonds. So review your valence shell electron pair repulsion theory, and that's easily done using this free resource, this OpenStax chemistry book. So getting back to our review, you need to focus on being good at drawing your structures. So this is the Lewis dot structure for ethane, but you need to know that we've got 4 electron domains around that carbon, and so that carbon is going to have a tetrahedral electronic structure around it. And so those angles are going to be 109.5 between the bonds, and these hydrogens are on top of each other. And so you want to draw them as close together as possible, because you need to see this rotation axis, this C3 rotation axis here. And so that's, if you rotate this by 1/3 of a turn, that's what the 3 means, then this hydrogen rotates down to this hydrogen. This hydrogen rotates back into that hydrogen, and that back hydrogen rotates up to this hydrogen. So that's a C3 rotation axis, and we'll look at that some more in a minute. You also need to be able to do the other kinds of hybridizations. Here, water, in acetone, this carbon here is sp2 hybridized. And so then the electron domains around that carbon there are trigonal planar. And that tells you also that this is a 120-degree angle. Yes, you need to know this. And you also need to know this not just so that you can answer simple questions on the test, like tell me what the carbon-oxygen bond angle is, but also so that you can determine the point group, which allows you to get the character table, use the direct product tables to come up with the selection rules for a spectrum. So let's define symmetry. Symmetry is defined as the number and types of symmetry operations that leave the object unchanged. And so if you operate on the object and you get the same shape and the same orientation as before, then you have that symmetry element. Notice the rotation here of these objects. You can see that that they're, well, what can I say about them? Let's just look at the symmetries of these different species. So which one of these, by this definition, is more symmetric? I asked this in class, and I was really pleased. A few people immediately said the sphere is the most symmetric, and that's true because it has the highest number and the highest types of symmetry operations that leave that sphere unchanged. There's an infinite number of reflection planes in a sphere. There's an infinite number of rotational axes in a sphere. It has an inversion center. It even has improper rotation, which is the rotation reflection operation. So the sphere has everything, and so it's the most symmetric object. But these other items have quite a bit of symmetry too, and you need to be very familiar with the tetrahedron and the octahedron because those are so common in molecular symmetry. These are the symmetry elements. These are the only 5 that you need to know. And so you could multiply the whole molecule's coordinate system by 1, essentially, and that's the identity operation. And essentially it's a do-nothing symmetry element, but every molecule, even the most asymmetric molecule, has the identity symmetry element. There's the n-fold rotation axis, which you rotate the molecule by 360 divided by n. So if it's a C3, you rotate it by 120 degrees. And there's mirror planes, and so you can look at yourself in the mirror and divide your body in half, and your left arm and your right arm are very symmetric, and so you can see that you have a mirror plane down through your body. That doesn't apply to your guts, but as far as external appearances, for the most part, you have a mirror plane. Then the inversion center, it inverts all objects through the point, and so if you have a molecule, which we'll see in a minute, we'll look at the inversion center. And then this improper rotation, or what some call the rotation reflection axis. This one is really confusing, so we'll just have to see an example of it in a minute. I put all of these definitions in here just to show you that just to have them in text form, but we're going to explore these in a minute. Let me say a note about operator algebra. The distributive law is obeyed and the associative law is obeyed. So you can distribute an operation through if you have a combined set of symmetry operators. So this might be a sigma reflection, and this might be a rotation axis, and this might be an inversion. And so you could distribute that through and have the inversion times the Cn of that function, and then you could have the inversion times the reflection of that function. And so this is okay to do. You can associate the two in different ways. So you could operate B on C and have that combined and then multiply on the function and then bring in A, or you could combine A and B and do C separately from A and B. So that's the associative rule. That's okay as well. But the commutative law is not necessarily obeyed. Sometimes accidentally or coincidentally it's obeyed, But in general, you can find exceptions, or you can find examples where the commutative law is not obeyed. If you wanted to see an example of yourself, here's one where if you operated with a C3 on ethane and followed that up with a reflection plane, a vertical reflection plane operation, you'd have different labels on the atoms than if you did it with the reflection in the vertical plane first and then followed up with a C3. If you are excited about this concept, then go ahead and prove that to yourself by labeling your atoms. Again, I put the definitions here in text form, but let's actually just go explore and learn by doing. So let's go to this Otterbein site. And so this is a fantastic resource for learning symmetry. And so there's several options here. You can do the tutorial, the gallery, and the challenge. We're going to go to the gallery, but later on when we're determining what point group a molecule is, you definitely want to work on this challenge page because you have the flow chart over here. And so you grab the molecular structure and you can take that molecule through the flow chart and come up with the point group for that molecule. This whole website is really here just to help you determine point groups for molecules. So let's look at the gallery and learn about their symmetry elements. Let's do ammonia first. So here's ammonia. I would typically draw this sideways like this. This would be a wedge here. So this part of the molecule I draw as a wedge, and there'd be a dash in the back, and I have an H on each of these. And then I have just a line showing that this nitrogen and hydrogen were in the plane by just a straight line. So that's how I would draw that molecule. And I would have the symmetry axis pointing straight up. So it's not exactly straight up, but it's pretty close. So that's how I would draw that molecule on the board or on my paper. And so let's rotate that axis. So when we rotate the molecule, we're rotating 1/3 of a turn around that axis. And you can see how all the hydrogens are exchanged with each other. So if I follow this hydrogen, it goes over to this one. If I start there, it goes to the back, and then the back, it comes to the front. We can look at reflection planes. Let's look at this one. So if I reflect it to the plane that contains that back hydrogen and the nitrogen, I'm essentially exchanging the two front hydrogens. So I'm reflecting, and those two front hydrogens are connected by this reflection operation. We have 3 of these planes, and they all just connect 2 different hydrogens. And so those are the reflection planes in the ammonia molecule. So that plane connects those 2, this plane connects those 2, and this plane connects those 2. So that's it for ammonia. It has a C3 axis and 3 reflection planes. So those are the symmetry elements that it has. Let's look at a molecule that has more symmetry. Let's look at ethane, but let's do the eclipsed form of ethane. Okay, so these hydrogens are on top of each other. I would draw it this way where the axis is vertical with respect to my piece of paper. I would draw those hydrogens as close as possible. There'll be a wedge on this front one and dashes on the back, same down here. And let's look at the rotation. So here we're connecting all 6 hydrogens to the others. We're also rotating the carbons, but they stay put because they're on the axis. Let's look at the C2 axes. These are perpendicular to the C3. It's really important to be able to identify that. And all the axes go through the center of mass. Okay, so we have 3 perpendicular C2s. And that's one of the questions on the flow chart. Do you have 3 C2s perpendicular to the C3? So we have the C3 here. And then we have these 3 perpendicular C2s. so we can rotate the molecule around each of them. Okay, so let's pick this one here. Let me turn the others off so we can see what's going on. Look at this rotation. We're rotating around that axis. You see how we're rotating 180 degrees. So 360 divided by 2 is 180. So we're rotating 180 degrees. And you can't tell I've done anything. That's the point. If we were to rotate this by 90 degrees, the molecule would be sideways. And I could tell I did something. A symmetry element, it only possesses the symmetry element if you can perform that symmetry operation and the molecule looks unchanged. The only thing that has happened to the molecule is that the labels have changed. So let's see if we can turn the labels on, the atom labels. I don't think so, but yeah, it doesn't look like we can. Yeah, but we can turn on the animation trails, and sometimes this is helpful because if the animation trails are on, it shows you the atoms that are connected with each other. And so that's showing you that these two hydrogens are connected with each other. This one went through this path, and this one went through the other path, and now they're connected to each other. This is really helpful when we do the S-axis. So let's look at the rotation reflection. In fact, let's look at that one in a minute. We'll do that with the staggered ethane. Next, let's look at the horizontal plane of symmetry. So we have the highest symmetry rotation axis. This little n, we say the highest n-fold rotation. So 3-fold rotation would be this axis here. This would be a 2-fold rotation. So 3-fold is higher than 2-fold. So 3-fold rotation is the highest symmetry axis. And we pick that axis and we look perpendicular to it. Is there a horizontal plane of symmetry? And yes, there is in this molecule because it's eclipsed. So if we reflect those, then that exchanges the atoms from the top and bottom. The carbons are exchanged and the hydrogens are exchanged. So notice the horizontal plane of symmetry is a unique plane of symmetry. It splits the highest symmetry axis and it's perpendicular to that. The vertical planes of symmetry contain that symmetry axis. So notice how they contain that symmetry axis. The horizontal plane split that axis in two. And so these are just very similar to those ammonia reflection planes. They just exchange certain pairs of hydrogens. And so those are the vertical reflection planes. There's the horizontal reflection plane there. And so I put that symmetry axis up so that the horizontal plane makes sense. It looks horizontal from our perspective. Let's now look at staggered ethane. So here's the sort of the Newman projection. See the hydrogens in front and the hydrogens in back. Let's flip it up. That's how I would draw it on the board or in my notes. So this hydrogen, the two carbons, and this hydrogen are all in the same plane. These hydrogens are in front and behind. So I would have a wedge here and dashes going to the back. I would have a wedge here and dashes going to the back. This has 3-fold symmetry, so there's our symmetry axis. Again, rotating all the hydrogens into each other. It has those perpendicular C2s, which are a little difficult to see in this molecule. They are perpendicular, but notice how they split the dihedral angles for those bonds. So let's look at one of those rotations here. Let's pick this one. And so again, it's the C2 axis. It's a 180-degree rotation, and you're just rotating it around each of those three C2 axes. Now let's talk about this improper axis. Improper rotation axis is the old word. I think now they call it the rotation reflection operation because it's rotation and reflection. And it's 6, so that means 1/6 of a turn. If I move this 1/6 of a turn, this hydrogen's going to come over here in the empty space. But it's right above that hydrogen. So if I rotate and reflect, it goes 1/6 of a turn and drops down and hits that hydrogen. So let's turn that one on and turn these others off. Okay, so we do this operation. It moves 1/6 of a turn and reflects through. Let's do that again. 1/6 of a turn and reflects through. This is a way to connect the top hydrogens to the bottom hydrogens by symmetry. The carbons also exchange. There really isn't any effect on the carbons from rotating, but there is an effect when you reflect it. So that's the rotation reflection operation. So I'm going to go ahead and turn on those trails, the animation trails, so you can really see how those hydrogens are connected to each other with this axis, with this operation. So you go 1/6 of a turn and then you reflect through. So this hydrogen goes 1/6 of a turn and reflects down to the bottom. This bottom one went 1/6 of the way and reflected up to the top. The carbons rotated 1/6 of a turn, even though you can't tell, and then reflected into each other. So that is the S6 axis. You see 1/6 of a turn and then you reflect through. Every atom in the molecule does the same thing. They rotate 1/6 of a rotation and then they reflect through that horizontal plane. Okay. So that is the improper rotation or rotation reflection operation. Probably one of the most confusing ones for students to see the first time they are introduced to symmetry. Let's now talk about the inversion center. Inversion, for some reason, is confusing, although I don't know why. It shouldn't be confusing at all. Everything goes through the center of mass to the opposite side of the molecule. And you can see if a molecule has an inversion center if you just pick an atom, go through the center of mass, and is there a same kind of atom exactly the same distance away from the center mass on the opposite side of the molecule. So let me invert this and you can see I still have the trails on, but this hydrogen is connected to that one through inversion. The carbons are connected to each other through inversion. This front hydrogen is connected to one in the back through inversion, and this back one is connected to this one in the front through inversion. So that's the inversion operator, and it does not have to be on an atom. It's on the center of mass. And so in this case, the molecule does not have an atom on the center of mass, and that's fine. It's not required. So those are all of the symmetry operations and the symmetry elements. You have rotation axes, you have planes of symmetry, and you have improper rotations or rotation reflection operators and inversion centers. So I would suggest that you pick these molecules over here and practice. So here's methane. Practice with methane. Start with ones you know. So methane, ammonia, here's water, okay? And then branch out and do some of these other crazy molecules. So here's the XZ plane, the YZ plane, the C2 axis. Not very much symmetry for water. That's why we call it an asymmetric molecule. And so I think with that, that's a good introduction. We can stop here and practice, practice, practice. You've got several things to do, and I'll come up with a homework assignment here soon where you're going to be drawing molecules. You're going to be providing in your own handwriting examples of the different symmetry elements and symmetry operations. And so get to know your Vesper shapes again, hybridization theory, local bond theory, so that you can come up with three-dimensional shapes of your molecules. And again, sorry for the glitch on the audio. Hopefully this was still helpful for you. Thanks.